Okay, so now if my lambda j's are just the variances in this new coordinates, then that means that lambda j measures the spread of the cloud in the direction vj. Okay? And so remember, our idea behind PCA is to say, keep only the directions that have the most variance. Luckily, I've ordered my lambda j's from largest to smallest. So the vj's are ordered in such a way that I get the most variance when I project onto v1, second most variance when I project onto v2, third most variance when I project onto v3, etc. So another way to view this is to say that v1 maximizes the empirical covariance of all the projected points that I get across all possible a's that have norm 1. That's what v1 is doing for me. It's saying, look at all possible directions along which you can project your point cloud and pick the one that has the largest variance. So somehow, this seems to be completely unrelated to the spectral decomposition that we used, but the spectral decomposition is actually finding that for us. And that's the magic of linear algebra, because if I actually told you, try to maximize this over all possible directions, it's a difficult task. There's a lot of possible directions you would have to look at and just find the largest one. And what the spectral decomposition is giving you, you can actually use those things which are implemented extremely efficiently. And you can actually now not have to search. You just compute the eigendecomposition. It just says, well, the eigenvector associated to the largest eigenvalue is actually the one that will maximize the sample variance when I project into this direction. Okay? And there's actually a very simple proof. So here, this is for the, well, here I wrote it for the, actually, there should be an S here. So let me put an S. Okay, so why is it S? Because I'm using PDP transpose, which is the spectral decomposition of S. Okay, so why is this true? Well, when I look at A transpose SA, this is A transpose PD P transpose A. That's just the spectral decomposition, which is just P transpose A transpose times D times P transpose A. Okay? So it's a vector transpose times D times a vector. And if I look at what happens when I do this, so let's call this vector, say, V, which is P transpose A. When I look at V transpose DV, what is this? Think about what happens when you pre and post multiply a diagonal matrix with this vector, okay? So it's going to be V transpose times your diagonal matrix with only things on the diagonal times V. Okay? So what's happening when I do this is that I get V1 times D times lambda 1 times V1, which is V1 squared times lambda 1 plus V2 squared times lambda 2 plus Vd squared times lambda d. Agreed? This is what happens when you pre and post multiply a diagonal matrix. But the lambdas are non-negative and all arranged in such a way that lambda 1 is the largest one. So lambda 2 is less than lambda 1, lambda 3 is less than lambda 1, lambda d is less than lambda 1. So this is less than lambda 1 times the sum for j equal 1 to d of the vj squared. But sum of the vj squared is really just the 2 norm squared of P transpose A. Okay? But P transpose A, so that's A transpose P transpose transpose, which is P transpose A. Right? That's the squared norm. But this is an orthogonal matrix. So this is the identity. So this is equal to A transpose A, which is the 2 norm of A squared, which we just assumed was equal to 1. Okay, so what we've computed is that A transpose SA is always at most lambda 1 times the norm squared of A, which is at most, which is equal to lambda 1. And so that means that if I look at the direction, the sample variance in direction A, it's always less than the sample variance that I get in direction V1. Okay, because if I plug in A is equal to V1, then I'm going to have, well, okay, V is maybe not the right thing I should have used. V1 is the largest eigenvector here, okay? So if I plug in A is the largest eigenvector, then P transpose V1 is actually equal to 1. Okay. So this is how we're going to do this. We're just going to try to find the directions one at a time that maximize the variance. So that we've done before, okay? So we said, okay, let's just say among all possible directions U, direction means just norm 1, try to find the one that maximizes the sample variance. And call this direction V1. And we just agreed that V1 is actually the eigenvector associated to the largest eigenvalue. Sometimes it's called the leading eigenvector itself. How do I continue this? Well, the key thing to continue is to find a second direction, U, which is orthogonal to the first one. So if I'm in 3 directions, I've picked this guy. This is my V1. And now I'm only allowed to look at directions that are orthogonal to this guy. And then I pick V2. And then if I'm in 3 dimensions, then the last one is actually already fixed for me. So I keep doing this, and it turns out that this notation, V1, V2, Vk, is not a mistake. It's actually precisely solved by the eigenvectors associated to the largest, second largest, third largest eigenvalues. Okay, so again, what's really nice about PCA is that you're actually looking for directions that carry most variance that are orthogonal to the ones that you found before. But you can actually, rather than searching through all those directions, the spectral decomposition is allowing you to get this immediately. You get all the V's at once. You get all the lambdas at once. You don't have to actually work too much on this, which allows you in particular to work with extremely large data sets. Now, those leading eigenvectors, when you're doing this in the context of PCA, meaning that those are the eigenvectors of your sample covariance matrix, those are actually called principal directions. Okay?